All right, welcome to the stream. This is day 7 of learning OpenGL. Today's topic is going to be the camera, which is actually the last topic in the getting started section. So I'm super excited about that. So let's just dive right in. In the previous chapters, we discussed the view matrix and how we can use the view matrix to move around the scene. We moved backwards a little. OpenGL by itself is not familiar with the concept of a camera, but we can try to simulate one by moving all the objects in the scene in the reverse direction, giving the illusion that we are moving. In this chapter, we'll discuss how we can set up a camera in OpenGL. We will discuss a fly style camera that allows you to freely move around in a 3D scene. We'll also discuss keyboard and mouse input and finish with a custom camera class. That sounds awesome. Camera or the view space. When we're talking about the camera or the view space, we're talking about all the vertex coordinates as seen from the camera's perspective as the origin of the scene. The view matrix transforms all the world coordinates into view coordinates that are relative to the camera's position and direction. To define a camera, we need its position in world space, the direction it's looking at, a vector pointing to the right, and a vector pointing upwards from the camera. A careful reader may notice that we're actually going to create a coordinate system with 3 perpendicular unit axes with the camera's position as the origin. So here it actually shows that this is the world origin, and in order for us to create a camera, the things that we're gonna need are the position of the camera, which here is 0, 0, and 2, and we're gonna need the z-axis, the x-axis, which will be the right hand side, and the y-axis, which will be the axis pointing up. First one is the camera position. Getting the camera position is easy. The camera position is a vector in world space that points to the camera's position. We set the camera at the same position we've set the camera in the previous chapter. So here we can actually just create a vec3 and we will just feed it or whatever we want the camera position to be. Don't forget that the positive z-axis is going through your screen towards you. So if we want the camera to move backwards, we move along the positive z-axis. So as it's showing here, if you want the camera to move back, that will be towards this blue axis. So that will be the positive z-axis. So that's why this z component is set to a positive number, that we were moving the camera back. Camera direction. The next vector required is the camera's direction. For example, at what direction is it pointing at? For now, we let the camera point to the origin of our scene, 0, 0, 0. Remember that we subtract two vectors from each other. We get a vector that's the difference of these two vectors. Subtracting the camera position vector from the scene's origin vector thus results in a direction vector we want. For the view matrix's coordinate system, we want its z-axis to be positive, and because by convention in OpenGL the camera points towards the negative z-axis, we want to negate the direction vector. If we switch the subtraction order around, we now get a vector pointing towards the camera's positive z-axis. Okay, so here it is showing that we are gonna need two things. First of all, we need to set where the camera is looking at, and in this diagram as it is showing, the camera is looking at the world origin, which will be 0, 0, 0. And then to get the direction that the camera is looking at, to get that vector, what we're going to do is subtract from the camera position the camera target. And then because we are just interested in the direction component and not the length of the vector, we're going to normalize it. That will essentially set the length to 1. The name direction vector is not the best chosen name since it is actually pointing in the reverse direction of what it is targeting. Alright, so because this, we're looking at the origin, but the vector that we're getting from this equation is actually going to point to the opposite direction. So it's that's why it's saying the camera direction or the direction vector is not the best name for it. Check this is fair. And then we're going to need the right axis. The next vector that we need is a right vector that represents the positive x-axis of the camera space. To get the right vector, we use a little trick by first specifying an up vector that points upwards in world space. Then we do a cross product on the up vector and the direction vector from step 2. Since the result of a cross product is a vector perpendicular to both vectors, we will get a vector that points in the positive x-axis's direction. If we would switch the cross product order, we'd get a vector that points in the negative x-axis. Okay, so as it has said before, that the cross product in a cross product, the order of the operands is important, and to get an up vector, we do a cross between. To get a right vector, we do a cross product between the up vector and the camera direction. So camera direction, we already calculated that, and the world up vector will always be 0, 1, 0. Okay, so that gives us the up vector. And now that we have both the x-axis vector and the z-axis vector, retrieving the vector that points to the camera's positive y-axis is relatively easy because there's also going to be a cross product. We take the cross product of the right and the direction vector. So that's it, the camera direction and the camera right. Cross producting those will give us the camera up vector. So now we are armed with the camera's position, the z vector, the right vector, or in this case the forward vector, the right vector, and the up vector. All right. Look at we got this. With the help of the cross product and a few tricks, we were able to create all the vectors that form the view of the camera space. For more mathematically inclined readers, this process is known as Gram-Schmidt process in linear algebra. Using these camera vectors, we can now create a look at matrix that proves very useful for creating a camera. Okay, so now we're going to create something called a look at matrix. A great thing about matrices is that if you define a coordinate space using three perpendicular or non-linear axes, you can create a matrix with those three axes plus a translation vector, and you can transform any vector to that coordinate space by multiplying it with this matrix. This is exactly what the look at matrix does, and now we have three perpendicular axes and a position vector to define the camera space. We can create our own look at matrix. Okay, so it is saying that if we have the three perpendicular matrices which we already calculated, the vectors, and a position vector, we also have that, we can actually create something called a look at matrix, and that can help us to convert any space into the camera space. Yeah, and you can transform any vector to that coordinate space by multiplying it with this matrix. Where r is the right vector. Okay, so these are the components of the right vector. U is the up vector. These are the components of the up vector, and D is the direction vector, and P is the camera's position vector. Note that the rotation left matrix and translation right matrix paths are inverted, transposed, and negated respectively. Okay, so we need to invert them, transpose them, and negate them. Since we want to rotate and translate the world in the opposite direction of where we want the camera to move. Okay, so that makes sense. We don't want the camera to move in this specific direction. We want the world to move in the opposite direction that supposedly we want the camera to move. That will give the illusion that the camera is moving in that direction. Using this look at matrix as our view matrix effectively transforms all the world coordinates to the view space we just defined. The look at matrix then does exactly what it says. It creates a view matrix that looks at a given target. Luckily for us, GLM already does all this work for us. We only have to specify a camera position, a target position, and a vector that represents the up vector in world space, the up vector we use for calculating the right vector. GLM then creates the look at matrix that we can use as our view matrix. Okay, so all of this stuff, we don't need to do that manually because GLM already does that for us. All we need to do is call the GLM lookat function and provide it with all of these vectors that we calculated previously. The GLM lookat function requires a position, a target, and an up vector respectively. Okay, so the position is this, the camera's position. The target position is gonna be the world origin, which we decided. And the up vector is just going to be 0, 1, 0 because that is the global up vector. This example creates a view matrix that is the same as the one we created with the previous chapter. Okay, but this time we're actually creating it through the GLM lookat function. Before delving into user input, let's get a little funky. By rotating the camera around our seed, we keep the target of the seed at 0, 0, 0. We use a little bit of trigonometry to create an x and a z coordinate each frame that represents a point on the circle, and we'll use these for our camera position. By recalculating the x and y coordinates over time, we're traversing all the points in a circle, and thus the camera rotates around the scene. We enlarge the circle by a predefined radius and create a new wave matrix each frame using GLFW's GLFW get time function. And that should rotate the camera around the scene. Okay, yeah, indeed it does. Okay, so let's try to do that. What do we have so far? Okay, so we just have a static scene where the camera is looking at the object. Okay, so these are the MVP matrices. We are right now dealing with the view matrix. Here we are actually creating it directly, but now what we want to do is create it through this. First, we're going to define a radius. So let's do that somewhere here. Okay, this is to do with the model. Yeah, let's do this here. Okay, the x is the GLFW get time. Multiply that by the radius. And I guess similarly we're gonna need a float cam y, which is the cos. Yep, cos, and we multiply that by radius as well. And it too is gonna be cos of GLFW get time. Okay, and then we create the view matrix, which we were doing up here. You can just bring it all down. GLMAT for view. Okay, so I guess in this case we don't need to initialize it. And then we're going to create a GLM look at, which will give us a mat4. So we're going to do GLM like 3, cam x 0 and cam z. Cam x gonna be 0 on the y and cam z. And then okay, the first parameter is actually the position. So because we're changing the position, okay, power just went out. GLM position, the second one is going to be the look at target, so that will just be 0 0 0, and the final one is the up vector. It's gonna be 0 1 0. Okay, what's wrong with cam z? It's actually cam z. Alright, so that should give us the view matrix, and then we are passing it normally to this. This is inside the render loop. Okay, yeah, that makes sense. Let's try that out. Okay, and it rotates around the scene. That's crazy. Right? Yeah, and it's also moved away from the center by the radius that we have set here. So if we decrease the radius, let's say we halve the radius, the camera is going to get closer to the world origin. Yep. Okay. So that's how that works. With this little snippet of code, the camera now circles around the scene over time. Feel free to experiment with the radius and position or direction parameters to get a feel of how this look at matrix works. Also check the source code if you're stuck. Okay, now we're gonna deal with walking around. Swinging the camera around a scene is fun, but it's more fun to do all the movement ourselves. First, we need to set up camera system, so it is useful to define some camera variables at the top of our program. Yeah, so we're gonna need to define the camera position, the front and up, and then we're gonna pass all that to the look at function. Okay, so it's saying at the top. I can just do that here right after GLM rotate. Let's do that here. First one is called camera pause. Okay, the power is back. Is equal to GLM web3. Camera position, I guess, is 0, 0, 3. Yep. Okay, camera front. Okay, the reason I'm typing all of this out rather than just copying it is so that it's easier for me to remember this. Camera front will be GLM vec3. Okay, so the front of the camera will be 0, 0, 1. Okay, 0, 0, minus 1. 0, F, 0, 0, minus 1.0. Okay, and then we have the camera up position. GLM vec3 camera up. And that's gonna be just the 0, 1, 0. Okay, so we have these defined, and now to create the view matrix, you can do GLM look at. The first one is going to be the position, the second one is the target, so that'll be the camera position minus the camera front. Okay. Here it's doing plus because camera front here is -1. And then the upper is just camera up. Okay, let's try that out. You can already tell these are camera variables. So rather than doing this, the matrix, rather than doing this, we're gonna pass it the camera's position, camera plus camera front, and then the camera up. Cool. First, we set the camera position to the previously defined camera pause. The direction is the current position plus the direction vector we just defined. This ensures that how it will move. The camera keeps looking at the target direction. Let's play a bit with these variables by updating the camera position vector when we press some keys. Okay, so whenever we're gonna update the camera position, the camera front is set to be 0, 0, -1, which if we look at this diagram would be somewhere around here. So it's kind of like saying always look ahead. We already defined a process input function to manage the GR. We already have this, so here we can set the camera speed first inside the input function, which is right here. Okay, this is set to 0.05. So if glfw get key, and then the key or this window is glfw key w is equal to glfw press then camera position plus equals camera speed times camera front. Okay, so to the camera position vector we are actually going to add the vector of camera front, but we are multiplying it by a scalar value which will scale it down, and that's how much it will move each frame. So whatever the current camera, these, whatever the current camera position is, we add to that camera speed times camera front. Okay, so all the other stuff will be similar. I guess to go backwards we will just subtract that, and to go right and left, what are we doing? Okay, we just have the camera front and the camera up, so we're going to take a cross product of that, and that will give us camera right. That will give us the right vector. So in order to go left, when we press the A key, we're subtracting that. Okay, so we're going to normalize it first to make sure its length is 1, and then we're going to multiply it by the camera speed. Okay, so if glfw get key and this window is glfw key A is equal to glfw press. So if this key is pressed, then camera position, we subtract that from. First we're gonna do a cross product. Okay, and I guess the order matters. First we're gonna put the camera front, and camera up. Yep, camera up, and then I'll give us the cross product, which will be the right vector, and then we need to normalize that using glm. What is it? Okay, yeah, small n, normalize. Okay, and then we scale that by the camera speed. Right, that wasn't so bad. Okay, so to go right, we'll just look for the D key, and then rather than subtracting, we'll just add to that. Okay, is that enough? Yep, that is indeed enough. Okay, this just looks beautiful. Okay, so I guess we're going to do camera rotation out of this. Whenever we press the WASD keys, the camera's position is updated accordingly. If we want to move forward or backward, we add or subtract a direction vector from the position vector scaled by some speed value. If we want to move sideways, we do a cross product to create a right vector, and we move along the right vector accordingly. This creates the familiar strafe effect when using the camera. Note that we normalize the resulting vector. Yep, that's fine. By now you should already be able to move the camera somewhat, albeit at a speed that's system specific, so you may need to adjust the camera speed. And finally, we have the movement speed. Currently, we used a constant value for movement speed when walking around. In theory, this seems fine, but in practice, people's machines have different processing powers. As a result of that is that some people are able to render much more frames than others each second. Whenever a user renders more frames than another, the user calls process input more often. The result is that some people move really fast and some really slow depending on the setup. When shipping your application, we want to make sure that it runs the same on all kinds of hardware. Graphics applications and games usually keep track of a delta time variable that stores the time it took to render the last frame. We then multiply all velocities with this delta time. The result is that we have a large delta time in a frame, meaning the result is that when we have a large delta time in a frame, meaning that the last frame took longer than average, the velocity for the frame will also be a bit higher to balance it out. When using this approach, it does not matter if you have a very fast or slow computer. The velocity of the camera will be balanced out accordingly, so each user will have the same experience. Alright, so we're going to introduce delta time here. I'm just going to make a float that will be 0 by default, and then we're going to keep track of the last frame. Within each frame, we then calculate the new delta time value for later use. Okay, so where do I define this? Delta time will just be 0, and we also have frame time, last frame equal to 0. And then within each frame, we then calculate the new delta time value for later use. So I'm assuming this calculation would be done inside the render frame at the beginning. No. Okay. Let's try to do this here. So we have a float current frame, which is equal to 0 to the get time. Get time, and then the delta time will be equal to the current frame minus the last frame. Alright, so far so good. We set the last frame to 0 by default because let's say this is the first frame, so last frame is gonna be 0. Current frame is equal to 0 to the get time, so the time since the application has started. So for the first time, delta time is just gonna be equal to the current frame, and then I guess we're just gonna set last frame to the current frame. Yep. Which I'm guessing should be done at the end of the frame. Last frame happens here whenever we call this function, and that will be stored here. So however long I guess this is fine, we can just do it at the top, and then however long all of this processing took, that will be added on to the next time when we call get frame, and that will be the difference between these two values. Okay, last frame is equal to current frame. So that should give us the delta time for each frame. And yeah, all we have to do is multiply the camera speed by delta time. That will also make it a lot smaller, so yeah, P is compensated for that as well, 2.5f. And now the speed of the camera should be frame independent. We're not going to see much difference here, but if the frame rate was variable, or if this was a slower machine, it wouldn't run any slower. Cool. So that was delta time. Since we're using delta time, the camera will now move at a constant speed of 2.5 units per second. Together with the previous section, we should now have a much smoother and more consistent camera system for moving around the scene. And now we have a camera that walks and looks equally fast on any system. Again, check the source code if you're stuck. We'll see the delta time value frequently return with anything movement related. Look around. Only using the keyboard keys to move around isn't that interesting, especially since we can't turn around, making the movement rather restricted. That's where the mouse comes in. To look around the scene, we have to change the camera front vector around to the on the input of the mouse. Okay, so camera front is always where the camera is going. So it makes sense if we change the camera front, the camera is actually going to rotate, or it's going to move in a different direction. However, changing the direction based on mouse rotation is a little bit complicated and requires some trigonometry. If you do not understand the trigonometry, don't worry, you can just skip to the code section and paste them in your code. You can always come back later if you want to know. Okay, I'm not that good at trigonometry. Let's see if I can understand this. Euler uses Euler angles are three values that can represent any rotation in 3D, defined by Leonard Euler somewhere in the 1700s. There are three Euler angles: pitch, yaw, and roll. So this is the pitch, the yaw, and the roll. The pitch is the angle that depicts how much we're looking up or down, as seen in the first image. The second image shows the yaw value, which represents the magnitude we're looking to the left or the right, and the roll represents how much we roll, as mostly used in spaceflight cameras. Each of the Euler angles are represented by a single value, and with the combination of all three of them, we can calculate any rotation vector in 3D. For our camera system, we only care about the yaw and the pitch. Okay, so the first two. So we won't discuss the roll value here. Given a pitch and a yaw value, you can convert them into 3D vectors. A 3D vector that represents a new direction vector. The process of converting yaw and pitch values to a direction vector requires a bit of trigonometry, and we start with the basic case. Let's start with a bit of a refresher and check the general right triangle case, one with the side at a 90-degree angle. So it's showing here that this is the cos of x, sine of x, and the hypotenuse is equal to 1. Cos theta is equal to x by h, and sine theta equals y by h. Okay, theta here is 90. If we define the hypotenuse to be of length 1, we know from trigonometry, so CATOA, that the adjacent side's length is cos of x by h. Okay, so that would be c cos of angle by hypotenuse is equal to cos of x by 1, because h is 1, so that cos x, and that the opposing side's length is sine of y by h. Okay, so will that be like SOH? Here x is, I guess, the base, and the O is this side. That'd be sine y by 1 equals sine of y. This gives us some general formulas for retrieving the length in both the x and the y sides on right triangles depending on the given angle. Let's use this to calculate the components of the direction vector. Let's imagine this same triangle, but now looking at it from a top perspective, the adjacent and opposite, A and O stands for adjacent and opposite. So here we have C and A is the adjacent. Okay, so this one is the adjacent side and this one is the opposite side. All right. Let's imagine this same, okay, from first perspective, side being parallel to the screen's x and z axis as if looking down the y axis. If we visualize the yaw angle to be the counterclockwise angle started from the x side, we can see that the length of the x side relates to cos of yaw, and similarly how the length of the z relates to sine of yaw. Okay, going up here, yaw is this. Okay, so we're looking top down, and here it is showing cos of x, this side, the bottom side. Okay, so if we visualize the yaw angle to be counterclockwise, so it's going in this direction, starting from the x side. Starting from this side, we can see that the length of the x side relates to cos of yaw. So how much we want to yaw, that will be this angle. Cos of yaw, that will relate to the length of the x-axis, which is this length of this axis here. And similarly, how the length of the z-axis relates to the sine of yaw, which will be this one right here. And that should give us this vector. So direction vector, we're going to set both the x and the z. Now that we convert the angle to radians first. Okay, this solves how we can get a 3D direction vector from a yaw value, but pitch needs to be included as well. Let's now look at the x. Now let's look at the y-axis side as if we're sitting on the xz plane. Okay, so this is the top-down direction. We're going to set the x and the z of the camera like this. We want to set the x and z using the yaw, and then the pitch value. What we're doing, we're taking the sine, which will be this pitch sine, that will give us the y. However, from the pitch triangle, we can also see the x sides are influenced by cos of pitch, so we need to make sure this is also part of the direction vector. With this included, we get the final direction vector as translated from yaw and pitch Euler angles. Okay, so this is the final thing. It's basically combining this for the yaw and this for the pitch. This gives us a formula to convert yaw and pitch values to a three-dimensional direction vector that we can use for looking around. We've set up the scene world so everything's positioned in the direction of the negative z-axis. However, if we look at the x and the z yaw triangle, we see that theta of 0 results in the camera's direction vector to point towards the positive x-axis. To make sure the camera points towards the negative z-axis, by default we can give it a yaw, a default value of 90-degree clockwise rotation. Positive degree rotates the counterclockwise, so we set the value to negative 90. You probably wondered by now, how do we set and modify these yaw and pitch values? Okay, so that will be by taking the mouse input. Okay, so first let's set this up. We need a direction vector. Then to combine these, this is the final thing. Direction.x is equal to cos of GLM radians yaw, which we haven't defined yet, and multiply that by cos of pitch. This declaration has no storage class specified. Maybe I should make it here. Let's put it somewhere here. Cool. Let's just define this stuff as well. Okay, set the direction dot y is equal to sine of pitch and direction dot z equals sine of yaw times cos of pitch. This gives us a formula to convert EI. I already read that, and it's setting the yaw to minus 90 by default. Now we're gonna need to take the mouse input. The yaw and the pitch values are obtained from mouse or controller joystick movement where horizontal mouse movement affects the yaw and the vertical mouse movement affects the pitch. The idea is to store the last frame's mouse positions and calculate in the current frame how much the mouse value changed. The higher the horizontal or the vertical difference, the more we update the pitch or the yaw values, and thus the more the camera should move. First, we will tell GLW that it should hide the cursor and capture it. Capturing cursor means that once the application is focused, the mouse cursor stays within the center of the window unless the application loses focus or quits. We can do this with one simple configuration call, GLFW set input mode, which I guess we should just do up here somewhere. After creating the window, we're setting this to current. Yeah, let's do this here. GLFW set input mode. In the window, GLFW cursor, GLFW cursor disabled. After this call, whenever we move the mouse, it won't be visible and it should not leave the window. This is perfect for an FPS camera system. To calculate the pitch and yaw values, we need to tell GLFW to listen to mouse movement events. We do this by creating a callback function with the following prototype. Okay, so just like we created a callback function for process input, we're gonna need to create a callback function for mouse callback. Okay, actually we create a callback for this buffer size, frame buffer size, not the process input. Okay, so mouse callback will be GLW window double X position and Y position. What's wrong with that? GLFW. Here, X and Y position represent the current mouse position. As soon as we register the callback function with GLFW, each time the mouse moves, the mouse callback function is called. GLFW set cursor position pause callback. Okay. Let's just do that here as well. Okay, wait, where are we setting this guy? Here. Here, I'm just gonna say GLFW set cursor pause callback. GLFW set. Okay, I'm just gonna add a comment here. When handling mouse input for a fly-style camera, there are several steps we have to take before we're able to fully calculate the camera's direction vector. Okay, how long have we been streaming? 50 minutes, 51 minutes. Cool. When handling mouse input for a fly-style camera, okay, so first thing we need to do is calculate the mouse's offset since the last frame, add the offset value to the camera's yaw and pitch values, add some constraints to the minimum maximum pitch values, and finally calculate the direction vector. The first step is to calculate the offset of the mouse since the last frame. We first have to store the last mouse position in the application, which we initialize to be in the center of the screen. So if it's 800 by 600, it will just be 400 by 300. Cool, let's do that. Oops, okay. So I'm just gonna add that here. Then in the mouse's callback function, we calculate the offset movement between the last and the current frame. So we know the last position, and here we know the current position. Rather than setting hard coding it to this value, why don't we calculate it from the window width? And the window height. Okay. So now inside the mouse callback, what are we gonna do? X offset and the Y offset. Is it float or W? Float. Will be equal to whatever the current position is. So X pos minus whatever the last position was, which is last X. And similarly for Y. Okay. Wait, what? Reversed since Y coordinates range from bottom to top. Okay. That was an easy mistake to make. Cool. Then we do last X equals X position. Okay, so for the next time, set these. Last X is equal to X plus. Const float sensitivity. Okay. X offset times sensitivity. Okay, so we have calculated these. Note that we multiply the offset value by sensitivity value. If you omit the multiplication, it would be just be too strong and filter the sensitivity to your liking. Next, we add the offset value to the globally declared pitch and yaw values. Okay, so we need to declare those globally. So to yaw, we're gonna add the X offset, and to pitch, we're gonna add the Y offset. In the third step, we'd like to add some constraints to the camera so users won't be able to make weird camera movements. Also causes a look at flip once direction vector is parallel to the world up direction. The pitch needs to be constrained in such a way that user won't be able to look higher than 89 degrees. At 90 degrees we get look at flip, and also not below minus 89 degrees. This ensure that the user will be able to look up to the sky or below at his feet but no further. The constraints work by replacing the Euler value with its constraint value whenever it breaches the constraint. Okay, so just checking if it is if it goes above 89, then we just set it to 89. And if it goes below minus 89, then we just set it to minus 89. So that's the constraint. Note that we set no constraint on the yaw value since we don't have, so we don't want a constraint on the horizontal movement. That's fine. The fourth and last step is to calculate the actual direction vector using the formula from the previous section. Okay, so we already have a direction vector, do we not? Okay, no, I think that, okay, yeah, here we go. Cos of Cherim radians, yaw, and cos of pitch. Well, we're doing that. Okay, yeah, it's the same thing. We also now just need to do the camera front. It will be equal to whatever the direction is, and we just have to normalize it. Wait a sec. Oops. So it's doing pitch and yaw, which is fine, and then we're changing the pitch and yaw whenever we move the mouse. So add that as well. Check it. Yep, this is working. I don't think it's tripping the camera at all. Okay, maybe there's another step. This computed direction vector that contains all the rotations calculated from the mouse movement, since the camera front vector is already included in GLM's look at function, we're set to go. If you now run the code, you'll notice the camera makes a large sudden jump whenever the camera first receives into focus. This causes, okay, wait a second. It's not working for me. Nope. Maybe I'm doing something with that incorrect order. Is the callback getting called? STTC out. Okay, it's been called. So this is fine. Then we're getting your page. We're changing that. We're only setting it here. We're not setting it again anywhere else. We're just using it. Okay, we're only using it once. We have to do it again and again and again inside our inventory. Okay, that will be the view. camera front. So we're gonna first calculate camera front and then we're gonna set it. Okay, now and we can fly around the scene. Crazy. All right. If you now run the code, you'll notice the camera makes a large sudden jump whenever the window first receives focus of your mouse cursor. The cause of this sudden jump is that as soon as your cursor enters the window, the mouse callback function is called with an X position and Y position equal to the location of your mouse enter the camera screen from. This is often a position that is significantly far away from the center of the screen, resulting in large offsets and thus a large movement jump. We can circumvent this issue by defining a global rule to check if the first time we receive input, if this is the first time we update the initial mouse position to new position, the resulting mouse movement will then use the newly entered mouse position by. Okay, this is fine. We just do this, and then the rest of the stuff will be the same. First, it will be true. Then it's setting to false. Cool. Yeah, don't have the second jump anymore. Alright, that's the whole code. Okay, wait a second. It's just doing all of this inside the mouse callback. I don't have to do it within the render loop. That is calculating the direction vector here. The process input is adding to the camera position. Which that should matter. Cool. So you can just take all of this. Put it in here. That would also mean it doesn't have access to the direction vector. Just pointer to that. Okay. And then we're setting the camera front value, which we're using here, and it's actually global value, so that should work. Still works. Alright, there we go. Give it a spin and you'll see that we can now freely move through our 3D scene. Zoom. As a little extra to the camera system, will also implement a zooming interface. In the previous chapter, we said the field of view, or FOV, largely defines how much we can see of the scene. When the field of view becomes smaller, the scene's projected space gets smaller. This smaller space is projected over the same NDC, giving the illusion of zooming in. To zoom in, we're going to use the mouse scroll wheel similar to the mouse's movement, and keyboard input will have a callback function to the mouse scroll. Okay, it also has similar stuff. Let's just do this quickly. We're gonna need to set an FOV. Okay, I think I am using some other FOV. Somewhere, I don't remember where. Yeah. When scrolling the Y offset, yep. Okay. Since 45 is the default value, we want to constrain the zoom level between 1 and 45. We now have to upload the perspective projection matrix to the GPU each frame, but this time with the FOV variable as its field of view. So projection is always perspective. Are we doing that? Somewhere here. Okay. Okay. Okay, we're not changing that each frame, are we? We're just setting it once. Projection. I just move this in here. Look. Might as well move the whole thing. Just get it back in order. Okay, so now this is changing every frame, and then we're setting it every. Okay, cool. Still on. Okay, I need to register the scroll. Yep, GLW to set scroll callback, and then we just give it the function. There we go. Okay, so this changes the FOV. I think we can go up to 90. That would be cool. Yeah, so we can zoom out and we can go. Cool. And there you have it. We implemented a simple camera system that allows for free 3D for free movement in the 3D environment. Feel free to experiment a little, and if you're stuck, check out the code. Okay, so we're gonna divide it up into camera class. Okay, we're almost done. In the upcoming chapters, we'll always use a camera to easily look around the scene to see the results from all angles. However, since the camera code can take up a significant amount of space on each chapter, we'll abstract its details a little and create our own camera object that does most of the work for us, and some neat little extras. Unlike the shader chapter, we won't walk you through creating a camera class, but provide you with a fully commented source code if you want to know the inner workings. Like the shader object, we define the camera class entirely in a single header file. You can find the camera. Okay, you just need to copy that. You should be able to understand the code after this chapter. It is advised to at least check the class out once as an example on how you could create your own camera system. The camera system we introduced is a fly-like camera that suits most purposes and works well with other angles, but be careful when creating different camera systems like an FPS camera or a flight simulation camera. Each camera system has its own tricks and quirks, so be sure to read up on them. For example, this fly camera doesn't allow for pitch values higher than or equal to 90 degrees, and a static up vector 010 doesn't work when we take roll values into account. The updated version of the source code is available. See if you can transform the camera class in such a way that it becomes a true FPS camera when not where you cannot fly, you can only look around while staying on the exit plane. Try to create your own look at function where you manually create the view matrix as discussed at the start of this chapter. Replace the GLM's look at function with our own implementation. It's like the same. Okay. So let's try this one. Oh, this is kind of weird. Okay, see if you can transform the camera class in such a way that it becomes a true FPS camera where you cannot fly. You can only look around while staying on the exit plane. When we are moving, let me see. What we're doing is we have the camera speed and we are multiplying that with camera front. So whichever way the camera is facing is where we're gonna move. But rather than doing that, we need to set this constant. Okay. I need to visualize this a little bit. So if this is the camera, really, like this, or let's say it's looking up, this is the exit plane. Right now we're taking this z-axis, the z vector, and multiplying that with the camera speed, and that's how we get where the next position of the camera is going to be. But rather than getting that, what we need is this vector, which will be the global forward vector. Not really. What I guess I could do is I could take the forward front vector and just ignore the y-axis, and that will essentially flatten this vector if like it has two components. Like essentially make it like this. Okay, let's try that out. Not saying that is the best way to do it, but I suppose that's a way to do it. That will be for moving forward, and yeah, it'll be the same for moving back as well. Yeah, so even though I'm looking up or down, I cannot go up or down. I am locked on the exit plane. So I guess that's what I'm going to do. Okay, but I just want to go back to this. All right, and then it's telling us to implement our own look at function, which I'm really not gonna do. Okay, I'm just gonna use the camera class that they've created. So it's the same. We have the camera movement. It's using it in Yum here. Default camera values. Yep, we already have those. So we have the constructor with scalar values. Process mouse scroll. So these are all the callbacks. Update camera vectors. Delete the front vector from the camera's updated all the values. Okay, what is it called? Camera rich. All right, let's include that here. Okay, so we're not going to need any of this stuff. Let's delete all of that. Okay, this is also going to look different. Don't need this or the scroll callback. Okay, this will also be different. We're just gonna get the delta time. Okay, so we still have delta time. Cool. And we're going to create a camera object, passing it the position of the camera. The last X, last Y, and first move are still going to be here. Okay, it's a lot better commented. Okay, what callbacks do we have? Frame, buffer size, callback. I already have that. We have the mouse callback, scroll callback. Okay. Why is it defining the prototype? Okay. It's setting the cursor and the scroll callback to this. It's probably defining it down here somewhere. Yep, it's defining it down here. That's fine. Frame size callback. We can do the same. Let's put all of this at the bottom. And then just put the signatures up here. All right. So for the camera object, okay, it has a different. What else are we doing? Screen width and screen height. I'm just calling it window width. Oh, I guess window width is more appropriate. Okay, it's doing the camera dot process keyboard and then just giving it the direction and the delta time. Okay, that is better. So I can just delete these. And inside here, like that. Forward, back, left, and right. Yep. Okay, that's fine. So we have to create the view matrix. We're doing camera.getViewMatrix, matrix, and that we're setting right over there. So all of this will be gone. We don't have the FOV, we'll have to get that from the camera. Okay, it's called camera.zoom now. Okay, so for the view, what are we doing? Get view matrix, and then we're just setting it in our shader. So we need to do this separately. Are there any errors? Okay, let's check that. Yep, still works as before. That's our camera class. Cool. I guess that's it for today. If you actually do want to follow along, you just need to click on the YouTube link and it'll take you to my channel where you can see all of the previous videos. We started from day 1 and today we have completed getting started section. So all of these videos will take you through all of this stuff step by step so you can easily follow them along. Right, so that's it for today's stream.